Archibald. I'm going to be talking about our use of RADseq to infer phylogenetics in these two genera of Asparagus. We're using this clade of Camassia and Hastings to look at processes of speciation and also methods of species delimitation. And I'm going to be talking today about our phylogenetic work, but this is part of a broader study. We're also looking at morphology, ecology, and reproductive isolation, so it's an integrated taxonomic study. And one of the reasons why this is a good group for looking at these kinds of questions is that it does encompass a range of levels and types of divergence. So we have forms that seem to be just beginning to differentiate to species that are highly distinct and have differentiated in a number of these factors. Another reason why this is a nice clade for these studies is that it has a complex taxonomy. So Camassia is a feasibly sized group. It has 6 species, but it also has 10 subspecies, and 8 of those are within just one species. So there's some questions there as far as the taxonomy goes. It has a disjunct distribution in North America, primarily in the US. So there's a center of diversity in the Northwest, and then a species complex that occurs farther east. Hastingsia is more narrowly distributed, and it's also a smaller group with as few as 2 species. But despite its tiny size, there's been a taxonomic dispute for decades as to whether there should be 1 or 2 segregates from each of those species, and recognized at various levels. Now, adding a little bit of urgency to these species delimitation questions, there are several members of both genera that are of conservation concern. So prior studies have shown us that these are sister genera, and their placement within subfamily. These 2 studies focused on the subfamily level, and the tree is from Archibald et al. Just zooming in here, Camassia is in blue, Hastingsia is in yellow. We also have nice support for the backbone relationships going into Camassia. There are a few points of conflict, and I'll come back to those. And there are also quite a few questions at species level that were not answered or resolved by these phylogenies, and that holds as well in these studies focused specifically within each of those genera. So we want to fill in some of that missing information, and to do that we're using a modified single digest method, or RADseq. We have 288 accessions in our libraries, and so far 128 of those have been sequenced, processed using PyRAD. And initially we're using concatenated Roxamel analyses to assess these data, but we'll be expanding that into other types of analyses. As with genomic data in general, there are a lot of questions as to the best method to process the massive data that you get off the machines. So we ran a suite of analyses across varying some of these parameters of PyRAD. The only one that I'll have time to talk about today is what I'm calling M. It's been known by various names, but it's just the minimum taxon coverage. So the minimum number of individuals that have to have a given locus for that locus to be placed within the data set. And obviously that connects pretty directly to the level of missing data in your data set, which has also been a source of questions with using RADseq at the phylogenetic level. Now these are just a few of the recent studies, the ones that have really focused on some of these parameters. I wanted to show you some comparisons to what we're doing, and also just quickly go over a couple of conclusions that are coming out. One is that you can get different topologies that are strongly supported despite their distinct relationships. And that's obviously a source of concern, but we're not talking about the entire phylogeny reshuffling. It's more that specific relationships are ambiguous. And what is probably not surprising is that those are often associated with short internal branches, so those have been problematic for phylogenetics in general. Another conclusion is that the optimal settings may vary across the tree, so not just between different taxonomic groups, but also within. Now, so in our clade, we're using these M values which correspond to 3 to 9% of those 128 individuals. And if you compare us to just a small sampling of some other studies, you'll see that we have many more individuals than some of these other studies, and also quite a bit lower sampling of those individuals per locus. I think that's a trend that we're going to see repeated in other phylogenetic studies as the breadth of individuals are expanding. But you may be wondering, why do we accept so much missing data in these analyses? And the short answer is that it's the only way to get a data set to analyze. So this plot shows that M value on the x-axis, the total go to those loci that are present in at least 4 individuals, we had 95,000 loci. That's that 3%. If instead we say that we want to only include loci that occur in at least half of the individuals, that drops down to 112. So obviously a really large drop-off here. And in fact, the maximum that we can get as far as coverage of individuals is 63%, and that's just one locus that has that much coverage. So clearly, reaching those complete data sets or nearly complete data sets is not an option, at least with this data set, with this group. Oh, there's one other thing I wanted to point out here, which is that we do see in that shaded region of parameters signal, phylogenetic signal. Hopefully I will convince you of that when I show you some trees here in a minute. And also, even though we focus within that region, we tried a few M values at higher levels. And as you might expect from the level of data lost in this phylogeny, that really led to a drop in the quality or apparent quality of the phylogenies. But in addition to our observations, you may be familiar with some recent studies that have looked at this in a computer-based way. And they similarly found that across their parameter space, the trees were actually more accurate if you accept more missing data. I would expect that there are limitations to that we have to explore on a case-by-case basis. So yes, we're seeing a very large impact of some of these parameters. In fact, if you read a study, you see the number of loci in that study. I don't think that that's necessarily very informative because that number can really change depending on your parameters. However, there are a range of parameters where we're seeing well-supported and consistent relationships, with a few exceptions. So like those other studies, we have a couple relationships that conflict between these different parameters. This subspecies here, Walpolii, is one of those. So it's monophyletic or it's not monophyletic. I think the main conclusion from this is just that this step of data exploration is very important for these kinds of studies to give us a feeling for what relationships are robust to these kinds of changes and which ones may be more problematic, and you can see if that affects the questions that you're trying to answer. So as I said, I do want to show you some actual trees. We are going to double the number of sessions in this data set, so we're not going to get too deep into the taxonomic conclusions, but I want to show you how this is working within Command Hastings. So this is the full tree, and I'm going to zoom in to different regions of this, but just a quick look overall, you can hopefully see that it is nicely resolved and supported. In all these trees, the black branches have greater than 90% bootstrap support, and the gray dashed branches have less than 90% support. So focusing first within that smaller genus Hastingsia, this one was completely unresolved in prior analyses, and now it's almost completely resolved, and strongly so. So this is a very nice step forward in understanding relationships here. And just a quick look through the taxonomy, we have the first species pair here. Each species is monophyletic. They're sisters, so you can split them and you come up with either way. It's supported by the phylogeny. The second species pair is the opposite. It's not monophyletic, but you split a little bit. And then moving on to the larger genus, again, overall, with an exception that I'll talk about, it's well supported and resolved. If we look at the larger clades, they're consistent with what we've seen in the past. And those points of conflict that I mentioned are now strongly resolved by these analyses. For example, Howellia here is sister to Lake Linnei. It was formerly sometimes placed there, sometimes sister to the remainder of the genus. So that obviously can have a big impact in our hypotheses as far as evolution within this clade. Another difference that was ambiguous before, or another relationship, was the placement of this disjunct clade, and again, strongly resolved. We do want to retest this because this is just a concatenated analysis, so we'll be looking at other analyses as well. And just to show you some of the lower level relationships, I want to focus within this clade. This is the Quamash complex, so it includes everything. Every taxon name in black is from the species Quamash, which is the one with 8 subspecies, and then also Pusicii is shown in tan, so you can see Pusicii is nested. Again, this is something we were unable to answer before. It was moving around. Basal clades consistent with what we've seen before, but all strongly resolved now. And this subclade here is the largest portion of the phylogeny that's not strongly supported. So it's that exception that I mentioned to having generally strong support. But it also also almost completely is made up of populations of this one subspecies. So it may not be surprising that we're not getting strong resolution of the tree at this level. There is, however, some strong support for the division of the subspecies, as there is for the division of Azuria and Walpolii, although that's the one that goes back and forth that I mentioned before. The last two subspecies in this clade are monophyletic, although I'd like to add some more populations to test that. And if we move down here, Breviflora, Quamash, Utahensis, they're all divided on phylogeny. So there's just not much support here for the cohesiveness of these subspecies. Obviously, that's something that we want to take a closer look at. Utahensis, the division of this subspecies here, was also supported by Sanger sequencing, and as you can see, it's not even lumping with other members of its species. That one may be due to integration, though. So if I'm going to return to shading here just to orient you as I zoom out. So here's the full Camassia tree with some clades collapsed. I just wanted to say one other thing with Breviflora, shown in yellow, which is that we also have two populations coming out much more distantly here in the Lake Linear clade. So in addition to the various resolution relationships that we're seeing, we also have the data pointing out some of these populations that may be worth a closer look. And each of those are strongly morphologically placed within the subspecies Breviflora. So, in summary, RADseq is proved to be a very useful tool within this group. It's resolving relationships across the various levels of interest for our study, from the generic down into these most of the interspecific relationships. We've been able to answer questions that we weren't able to answer before, as far as basal relationships and the species complex relationships in particular. And there are many people that I'd like to thank for this, and I'll take questions. Thank you. Yeah.
How did you estimate your trees?
We use RexML, concatenated analysis.
I might suggest that you try a quartets method. So if you have a lot of missing data and you are using them and cut off, let's say 4, you actually will have a lot of information content that might help with some of those clades, but also just avoid the concatenation across the entire data set.
Yes, thank you. That's actually next on our list.
Okay.
So I agree, that's a very useful method. We also did some subset analyses with RexML, just thinking about trying to do it across the entire phylogeny, which gave us very consistent results, but we haven't gone beyond that yet.
The other thing you might try is when you process your data, break it up into smaller groups rather than, I don't know how you did it, but if you did a global analysis across the entire phylogeny to process the data, you might actually retain or pull out more information if you do it on smaller groups. Because there's a lot of dropout based on evolutionary distance in that seed, and you might cover some more of those sides.
Yeah, we did that at species level.